I would like to relate the concept of HDFS with a short story so that it will be easier to understand. If you have already seen my previous video, you might know the story. I'll link the video in the description. You can go and watch that. So just let me give a brief description of the story. There was a businessman on a small town. He used to keep his goods in a small store. As demand increased over years, his store was not enough to handle the storage. He had to keep more products but was having limited space. So he rented a nearby space. Also, he hired one worker to take care of that space and the products in there. When he needed any product from the new space, he would just call the worker over there and ask him to deliver the product. This way, every time he faced a storage issue, he rented a new space and hired one worker to take care of that. HDFS works just like that. It works based on master-slave concept. The main components of HDFS are name node and data node. As the name signifies, the data node holds the actual data, whereas the name node handles the metadata information. Just like the businessman, when a customer comes and asks for some product, he will call the respective worker to deliver the product. Similarly, name node maintains the metadata information. That is, it keeps a record of which data files are in which data nodes, so that when there is a request to process data from a specific file, the name node will have the information about the location of the file. Now it is a owner's responsibility to organize the request and redirect it to respective store. Something like if a customer requests for, let's say, vegetable oil, perfume, potato, onion, rice, dishwasher, ice cream, soft drinks, etc., then it's the owner's responsibility to organize the products based on the store which holds it and send the respective request to the store in charge. Once everything is ready, it will be organized into a package or multiple packages and will be delivered to the customer. When a client hits the master node with some request, it redirects the request to respective nodes. Now let's suppose there is a file a.txt in HDFS and a client wants to get the data in a.txt to perform some analysis. The client will not have any idea in which node this a.txt file resides. So it will approach the master node, that is name node, with the request. Now the master node will analyze the request and command the respective slave node for the requested data. Once the data is ready, the client will be notified and now the client can get requested data. By now you know about two types of nodes in HDFS, that is master node and worker or slave node. There are 5 services in HDFS: name node, secondary name node, job tracker, data node, task tracker. Top 3 are master services, or you can say master daemons, and bottom 2 are slave services or slave daemons. Daemon means a background process. That means these services we cannot see them, but they are running internally. Master services can communicate to each other, and so as slave services. The corresponding slave node for name node is data node, and same way the corresponding slave node for job tracker is task tracker. So name node can communicate to data node and job tracker can communicate to task tracker and vice versa. But name node cannot communicate to task tracker and job tracker cannot communicate to the data node. Now let's talk about how data being stored in HDFS. Let's say you have a 150 MB of file that you want to save to HDFS. Apache Hadoop distributed file system has a default block size of 64 MB, which can be changed. For a conventional file system, the block size used to be in KBs, like 4 KB or so. Block is the minimum amount of data that it can read or write. In a conventional file system, let's say the block size is 4 KB. Now if you want to save a 1 KB file into the block, then also it will occupy 4 KB of disk space. But that is not true in case of HDFS. If a HDFS block is of 64 MB and you are storing 30 MB of data into that, then the rest 34 MB will be released for other files. Right now you might have a question why the block size in HDFS is so big. Well, the obvious answer is as it handles big data. HDFS is a file system designed for storing very large files that are hundreds of gigabytes or more in size. It is built around the idea write once and read many times pattern. A dataset is typically generated or copied from source, and then various analyses are performed on the dataset over time. Each analysis mostly involves a large portion of the data, so the time taken to read the whole dataset is more important than the time taken to read the first record. Hadoop doesn't require expensive, high reliable hardware. It's designed to run on a cluster of commodity hardware. That is, commonly available hardware that can be obtained easily. As it uses cheap hardware, so the possibility of node failure is high. But HDFS is designed to carry on working without noticeable interruption to the user in case of such failures. So, coming back to the storage process. You have a file of 150 MB and you want to store it in HDFS. So now your 150 MB file will be divided into 3 input splits, having 2 splits of 64 MB and 1 split of 22 MB. Now the name node will check which data node is having available storage space to store the splits. Once name node identifies appropriate data nodes, it will tell the client to save the splits into the corresponding nodes. Now, as we have already discussed, Hadoop runs on cluster of commodity hardware, so the chances of node failure is very high. Let's say the client has saved its data to data node 1, and because of some issue the data node 1 failed and stopped working. In that case, all the data present inside data node 1 will be lost. This can cause huge problems. So to avoid such problems, HDFS keeps replica of each input splits. So in case of one node failure, the data can be retrieved from other nodes. By default, the replication factor is 3. That means there will be 3 replicas of each input split. So as client store its data to node 1, in turn it will be replicated in 2 other nodes. Let's say from the name node, client received an information like the data of first split will be saved into data node 1, data node 5 and data node 7. In that case, client will save the data into data node 1 and then slave node 1 will request slave node 5 to duplicate the data into data node 5. Same way again, slave node 5 will request slave node 7 to duplicate the data in data node 7. All the slave nodes sends heartbeat and block reports to the master node in every short time interval. So once the master node gets the block report, it will know about the status of input splits in respective slave nodes. And thus, name node will update its metadata information based on the block report. Thus, name node will have information about where the first input split is present. The same process will be followed for other splits as well, and the metadata information will be saved in name node. Now let's say for some reason slave node 1 failed. In that case, all the data in slave node 1 will be lost and it will not send any more heartbeats to the master node. As master node will not receive any heartbeats from slave node 1, it will consider that slave node 1 is down. Thus the data in slave node 1 will now have only 2 replications. So to make it 3 again, the master node will duplicate the blocks present in node 1 in other appropriate nodes. Once node 1 issue is resolved by administrator and connected back to the cluster, the node will have no data and it will start as a fresh node. So now I think it will be easier for you to understand why Hadoop is keeping block size as 64 MB or higher. Let's say your block size is 4 KB and you want to store a file of size 1 TB. So how many input splits will be created? 1 TB divided by 4 KB numbers of splits. That is almost around 250 millions of input splits. Now let's say you have a replication factor of 3. That is, each input split will be duplicated and stored in 3 different nodes. So the total number of input splits metadata that the name node has to keep track of is 250 millions into 3. That is 750 millions, which is a lot for a 1 TB file. Some clusters keep data in size of PB or QB. In that case, the amount of metadata that name node has to manage will be beyond the hardware processing capacity. Now let's see what will be the difference if we are using 64 MB of block size. Same 1 TB of data, so number of input splits will be 1 TB divided by 64 MB, which will be around 15 to 16,000. Let's suppose it's 15,000. So now we'll have 3 replicas of 15,000 input splits. So the total number of files that name node has to keep metadata of will be 15,000 into 3 equals 75,000, which is much smaller and achievable compared to 750 millions. This is why in some large clusters where there is more data, they used to keep block size as 128 MB or even 256 MBs. Okay, so now let's discuss about name node failure. Let's say for some reason your name node went down and you lost all your metadata about the files in HDFS. Now what will happen? Will you be still able to use the data in the cluster? The answer is no. Name node is the single point of failure for Hadoop. If name node fails, then Hadoop will not have any information about which file splits are present in which nodes. So even if you will have all the raw data, it will be unusable. You will have no idea about the location of the file splits. This is the reason name node always uses high reliable hardware. 1 GB of space in name node is well enough to hold few millions of input splits information. As a rule of thumb, we used to allocate 1 GB of name node space for each 1 million blocks when replication factor is 3. Let's say you have a cluster of 200 nodes. Each node is having a disk size of 24 TB. So the total size of cluster is 200 into 24 TB equals to 4800 TB. If your block size is 128 MB and the replication factor is 3, then the memory you need in your name node is 4800 TB divided by 64 into 3 MB, which comes around 12 GB. So 12 GB of name node memory is good enough for a cluster of 4800 TB with block size of 128 MB and replication factor 3. So now let's discuss about the precaution taken to avoid the data loss during name node failure. There is a concept of secondary name node. Don't get tricked by the name. Secondary name node can never work as a backup in case of primary name node failure. Secondary name node only takes backup of primary name node in a regular interval. So in case of primary name node failure, another node can be installed and metadata can be copied from secondary name node to the newly installed primary name node. There are hardly some cases where there is a name node failure, but still precaution is very important. As name node uses high reliable hardware, unlike commodity hardware in case of data node, the chances of node failure is very low. So till now we have understood about how we save data in HDFS, how it gets splitted and saved in HDFS, also the methodology followed for handling data loss. So now let's discuss about the method followed to read data from HDFS. Let's say we want to calculate the number of online transactions taken place for a big bank in last 1 month. Usually the total file size would be something in PB and distributed over a cluster of hundreds of nodes. But for our easy understanding, let's suppose the file size over which we'll perform the calculation is of 150 MB and is distributed over a cluster of 6 nodes. So the 150 MB file will have 3 input splits. Each input split will be duplicated 2 times to have 3 replicas. Let's say the first split of 64 MB present in node 1, 2 and 5. Second split of 64 MB is present in node 3, 4 and 6. And third split of 22 MB is across node 2, 3 and 6. When a client wants to perform calculation over this file, first it has to come to the master node, as name node will have the information about the location of the splits. Once the client submits the code for doing some calculation, job tracker from master node will have the code or logic it has to perform over the input splits. So now job tracker will take the information about the location of the splits, and as job tracker can communicate to task tracker of slave nodes, it will send a request to task tracker to perform the calculation on the file that its data node contains. Now task tracker will run the code on proper input splits. This process of task tracker doing computation is known as mapping. So now in our case, job tracker will request task tracker from node 1 to do mapping for first split file. Similarly, it will request node 3 and node 2 for mapping second and third splits respectively. Let me give you one example. Let's say you want to travel from point A to point B, and there are 3 possible routes that you can opt from. First, route 1, that is 5 km, straight to your destination. Second is of 7 kilometers, and the third one is of 10 kilometers. So when you will be given with a choice, which route you will choose? Obviously 5 kilometers, right? Same way, job tracker always tries to assign task to the task tracker that is near to minimize the latency. But now let's say the first route is having high traffic. That might be 5 kilometers, but because of the traffic, it will take you long to reach at point B. So an obvious choice at that time will be route 2, even if it is little bit longer. Same way, when there is traffic on nearest node, that is, let's say there are already 100 jobs on queue for nearest node. So if you submit your job to that node, it will be the 101th job. So instead of that, job tracker will assign the job to other node that's having the same split file and less traffic. Okay, so now back to mapping. Job tracker submitted job to the node 1, 2 and 3 for doing the calculation. So each node did their calculation and returned the result for their respective splits. So right now we'll have 3 files from 3 task trackers. But that is not the final result. Let's say you are having a big file with 5000 of input splits. So in that case, you will get 5000 outputs, and it is not at all feasible to analyze 5000 result files. So we have reducers. It will combine outputs from mapper and give you a result file. There can be one or multiple reducers. By default, it is 1. How many numbers of reducers are there? That many numbers of output files will be generated. Let's say there are 5000 input splits. So you will have 5000 result files from mappers. Now reducer has to combine all the files to one result. If we are using single reducer, it will take long time to get the final output. On the other hand, if we can assign 5 reducers, each working on 1000 files to give output, that way it will be much faster. And each reducer will give one result file which will contain result from 1000 mapper outputs. So right now we understand number of input splits equals to number of mappers. That is, how many number of input file splits are there, that many numbers of mappers will be there. And number of reducer equals to number of output files. So now once all processing is done, name node will get update from data node through block report that the output files are ready and present in some data node. Once it gets the update, it will notify the client that your result is ready. So this is how reading and writing happens in HDFS. In our next video, we'll discuss about MapReduce. There you will have more insight about the reading process. So if you like the video, please hit the like button, and if you are new to the channel, consider subscribing. Don't forget to click the bell icon so that whenever I post a useful video, you'll get notified first. Thank you for watching the video. Signing off for now. See you on the next video.